you can say it will be there in as well. So I would like to request Dr. Kahng his presentation. I think. Yeah. Thank you and welcome to all the participants. Welcome.
So the introduction is over.
Sir Kahng, now you can start your presentation. We all are waiting for your presentation. Please go ahead.
Hello. I'm Sungtek Kahng, as introduced by Professor Amit Singh. But fortunately, I could see him at several international conferences to have a very pleasant conversations regarding metamaterials and very brilliant applications, including CUBE satellites. What I'm lucky to be here to give the things I have developed until now. I clearly think most of you have done a lot of great jobs under the name of 5G communication systems or circuits or millimeter wave circuitries or systems or whatever. What they are really helpful to the pedestals for industrial success stories. Though the title, first page a little different from what you have introduced to, but the contents and the backbones I'm going to share with you through this talk are the same. You can get relaxed and lay back to enjoy my talk. Sungtek Kahng, on behalf of my research staff, Ching Lee and Heejun Park, Wang Yu, Nam Gung, and Yejun So, or the other guys, they are really instrumental in achieving what I had to develop for the industrial purposes or objectives. Let me move on. Can you see this picture? That's fine? Professor Amit, yeah, can you see an array of pictures here? Yeah, hopefully you can see, you are able to see these pictures. I took these pictures last year in India and Korea, where very prestigious Indian experts got together for having really constructive conversations and constructive discussions to exchange our thoughts and ideas. That was really amazing. So I left you with part of my memory about India. And also another slide shows you the photographs I took with my new friends from India, and I could happily visit the shrine for Mahatma Gandhi. So that was really memorable. Apart from researchers I have bumped into through the conferences or activities, I could feel the atmosphere or very sacred atmosphere of the shrine for Mahatma Gandhi. Let me tell you briefly where my city is located. That is Incheon, city of Incheon, which is the gate city to foreigners from India and other countries. You should visit Korea through Incheon, and this is the map where Korean Peninsula is located, right next to Japan and China and Russia. And you can see the bird's eye view on the campus of Incheon National University, especially this building, which has my office. Cut to the chase, I'm going to the outline of my talk. We are going to see what 5G wants, but this is already not very new, because everyone has been exposed to what 5G wants or what kind of blueprints we are going to draw under the name of 5G. And that was is going to be done in section number 1. And section number 2, I will briefly describe what metamaterials are, especially their key features for circuit designs, antennas, or metamaterial superstrates, whatever they are going to be used or possibly adapted to the 5G or beyond. Then I'm going to move to the detailed parts of the examples of metamaterial circuits, antennas for 5G systems for the purpose of beamforming, dense MIMO antennas, and metamaterial components. And finally, I will come to the conclusions. So the first thing we should see is what we are going to achieve through 5G service. So 5G mobile service has this blueprint. There are 2 pentagons. The nodes, the 5 nodes of these pentagons tell us what we are going to experience under the name of 5G or in the 5G era. As you already have been familiarized with, ultra high speed and low latency is one of them. The others are massive connectivity and energy cost efficient infrastructure, an intelligent flexible network, reliable secure operation. And you can add more subtle or detailed things to these pentagons, but I can summarize what we are going to accomplish through 5G mobile networking. Let me move on to next slide. You can see actually in many white papers or blue papers on 5G, what conducted the research or the survey or research has been done by the world renowned the mobile companies or handset developers or base station antenna developers. From their points of view, what they and what we pursue look very similar to each other. We would like to give the function to the base station antenna to shine the electromagnetic wave to the users who are mobile. So point to point, hopefully point to point connectivity between the BTS or base station antennas to the mobile users, which will suppress the interference between you and the other users like that, and fast data transmission, which is enabled by the millimeter wave regime and the vehicular. Excuse me? Excuse me, that's fine? Yeah. Yeah. So what you can see the connectivities here. So I'm not going to spend much time in describing this because what they pursue in 5G is quite crystal clear. Yeah. I picked up several example pictures. Yeah. Some of them are related, deeply related to 5G, which are ongoing, but the others are the supporting technologies which could. Yes, somebody should turn it off. Yeah, the microphone should be turned off. Is that okay? Can I move on? Yeah, you can see this person advertises the 5G antennas on behalf of Samsung Electronics, and this model is advertising the handset for 5G in Korea. And you can see what the very interesting feature provided by the 5G handsets to be, and all these things have been developed through the era and the beginning given by Mr. Martin Cooper, who suggests the first, who proposed the first cellular phone in the world. Since then, the development of mobile communication systems has been accelerated, as you know. If we would delve into what's inside or as the layout of the handsets under the name of 5G, you can see, but actually this picture is already outdated. There are several new pictures which advertise how the 5G millimeter wave antennas are going to be laid out in the platform of handheld devices. But just a few years back, this picture was used and referred to quite a lot, quite frequently. But the basic principle has not changed. Well, even though they are not going to adopt 2x4 but actively calibrated antennas for the time being, they are going to use 1x4 millimeter wave antennas embedded in the platform of the handsets. And actually what this antenna, this is an array antenna, which is quite similar to what you can see from the top of this antennas in package or AIP, but they are the same for the function. And not only the handset antennas, but also you can see the candidates for the base station antennas or repeater antennas as the infrastructure to link between a transmitter and the receiver. And I brought this picture from one IEEE journal where the 2x4 radiating elements are excited by the RFIC. In the past, we could separate the radiating elements from the feeding structure such as the RFIC, but these days they come together. So instead of separating the radiating elements from the RFIC or feeding, active feeding structure, these days, we handle these two blocks at the same time for 5G communication. Let me move on. The definitions or the features of the metamaterials. But this picture, some of you might be familiar with this picture because I have done similar presentations in the IEEE India webinars before. So the patterns were quite attractive when the dancers were performing on the stage in INCAP last year. So I brought this picture from the gallery of my photographs, and I took another picture from the wallpaper. Wallpaper itself tells us kind of a reflector array, which changes the diverging wave to the very highly directive far field pattern. This is easily found on the household, on the walls of the households. Yeah. Well, apart from the material patterns, I would like to state the features of the metamaterials or from the summarized pictures. So you can see a gallery of pictures which are categorized into 4 things. Here, what this is kind of a resonant based, metamaterial resonant based component. And the second category or second column includes couplers, including power dividers or hybrid branch line couplers. The third category tells us small antennas which use the zeroth-order resonance, which can be the key to the size reduction or miniaturization. And last thing is you can change the direction of the wavefront, shape of the wavefront or direction of the beam of your antenna, such as the superstraight or metasurface, superstraight or covers. So I could divide the world of the metamaterials into 4 categories overall. But 4 key features are shown here. The first one is, well, when we have to deal with the effective epsilon and effective permeability, they are less than or 0, sorry, they are less than 0 or they are equal to 0, you can expect some bizarre phenomena compared to the conventional physics. Actually, everything belongs to physics. You can twist the angle of refraction from positive to the negative like this. If you make your permittivity and permeability negative, well, this is what you can expect. And nonlinear dispersion curve is usefully adopted to reduce the size of the circuits or components due to the linearity between the omega n phase. This is the omega axis, and this is the phase axis. Well, if you have a linear property of dispersion. Yeah, so this nonlinear curve brings us the effective size reduction of your structure. So metamaterials do not always include only metasurfaces such as metamaterial lenses. Circuits can be designed on the basis of the concept of metamaterials, such as zeroth order resonance, which I'm going to introduce to you right now. This is the electric field plot of a filter. This is what third order bandpass filter. At the center frequency, we intended to create the zeroth order resonance frequency or non-phase variation of the electric field from input port to the output port when it passes the signal at the center frequency. This is what we can get under the name in terms of electric field. So this is the typical phenomena of the zeroth order resonance. So all these 3 blocks have zeroth order resonance phenomena. So when they couple them, you can make an entire zeroth order resonance structure like this. And so zeroth order resonance field behavior should be observed in your metamaterial circuit. And sub-wavelength size, that means the unit cell or entire structure of the metamaterial should be much less than quarter wavelength. So my filter, which works at 120 megahertz, which is very smaller than my palm, and when it is compared to the edge coupled bandpass filter of the same order, this is much smaller or shorter than the conventional third order filter. This is what you can get. I'm going to happen to talk about the sizes of the circuits I have designed under from the standpoint of zeroth order resonance or negative resonance mode. So I'll skip this to the next page. As you already have seen from many textbooks or many journal papers or literature, you can make the basic components or basic structures for epsilon negative and mu negative. Yeah, the top left, you can see an array of split ring resonators, which is well known for making a negative mu phenomenon. And on your right hand side, top right, you can see an array of metallic rods. So you can tune the frequency of operation of this metallic rod. The effective epsilon becomes negative. So these phenomena can be modeled with the Lorentzian curves for mu r and epsilon r. So what epsilon negative and mu negative respectively makes your structure kind of a bandstop or electromagnetic band gap structure. But if you mix them together, the split ring resonators or mu negative material and the periodic metallic rods as the epsilon negative material together, this is what you can see. This is what you can see, and this area especially, you can see these this dispersion or diagram, especially the constitutive parameters such as epsilon and mu for horizontal and vertical axis for this diagram. Especially the conventional materials belong to the first quadrant where epsilon greater than 0 and mu greater than 0, which is called double positive material or DPG or DPS. And simultaneously, when epsilon, mu and epsilon both are below 0, you can make the double negative material DNG or left-handed material. This shows you a very interesting phenomenon, which is sketched by this arrow. This arrow tells you this is the point of source and that this is the point of observation. From the distance grows, as the distance grows from the source, actually the energy propagates or is propagated from the source to the point of observation. Meanwhile, the arrow of the phase vector goes reverse. So this occurs from the double negative material region. This is the negative epsilon and the negative mu region. But not only these two quadrants, actually we sometimes use this area too. Why? Mu r less than 1, but positive. Epsilon r below 1, but positive. These two, this area, mu r less than 1 and epsilon r less than 1, make your antennas or unicells of the metasurfaces can be very small too. So you can extend your points of view from just double negative area to mu r less than 1 and epsilon r less than 1 simultaneously. I'll skip this because everyone knows this. Yeah, can you see the animated electric fields here? Yeah, there are two pictures. These two pictures represent double negative frequency behavior and double positive frequency behavior. If you refer to the dispersion curve like this, can you see this dispersion curve like this? What pure right-handed material has the linear dispersion curve, and pure left-hand material leads to this hyperbolic curve, which tells us beta negative, and it belongs to beta negative, and it is no more linear. If you combine them together, well, which is called the CRLH or composite right and left-handed properties, you can make this kind of discontinuous curve, or this is continuous curve. I designed a Vhf filter, which includes double negative region just below the center frequency of the passband, and the double positive region just above the center frequency, which is the zeroth order resonance, like this. The dispersion curve looks like this curve, the pink curve on the top right. this is a very interesting phenomenon. What intrigues you here is, this is a port 1 and this is a port 2. If you inject the microwave energy into the port 1, energy moves from port 1 to port 2, but the phase moves from port 2 to port 1 like this. So this is one of the ways to check whether your metamaterial designs are right or wrong. And at the same time, this frequency, this observation of the field was done at the intended double negative frequency. And at the double positive frequency, we can see this is quite familiar to you, or you feel it quite natural to you, because the right-handed materials are everywhere in the neck of the woods. So here, this is port 1 and port 2. Likewise, if you inject the microwave energy here, then energy moves from port 1 to port 2. And phase front moves the same direction. This is called what we call the right-handed transmission line property. Meanwhile, the top left picture tells us this is a left-handed propagation property. Let me move on. And you can observe other features of metamaterials. This is the what we have 3 different regions which are explained as, this is the air, n equal to 1. N here means refractive index, and the second region, or this slab, is the double negative material, or negative refractive index material, and it is followed by another air. So you make a horn antenna. This is the feeding point of the horn antenna. Energy starts from here, starts at here, and propagates to the air through the aperture of a horn antenna, and the wavefront hits the surface of the double positive and the double negative material. The angle of refraction becomes negative like this. In a natural or the conventional material, you expect the angle of refraction this direction, but here n equal to -1, so the refractive indices are matched in terms of magnitude, but the signum or signs of the materials are opposite. So we can expect the reversal of the sign in the angle of refraction, and the energy goes on and goes on. But you can get kind of illusion here. Electromagnetic wave moves from right to left, but the phase front moves in that direction, but energy is propagating from left to right. So it hits the interface between the negative refractive index slab and positive refractive index slab. Here you experience another reversal in the direction or sign of refractive index. So you can see this, the direction of the ray goes here. So you can observe 2-time reversal in the sign of angle of refraction. And we designed a bandpass filter here. This works at a UHF band. You can see the structure, and this is the electric field plot. So from port 1 to port 2, energy is injected to port 1. It is propagating to port 2, but phase front, energy moves from port 1 to port 2. But if you keep observing the direction of the phase front of the electric field, that moves from port 2 to port 1. So the reversal in the direction of the phase front represents feature of the metamaterials. So this only happens with the beta or wave number negative. Let me move on. And you can tilt the beam when you put the double negative prism here. So this is the waveguide, which is connected to the kind of just half diagonally cut waveguide. And the beam is moving, but actually the diagonally cut waveguide area is filled with the double negative material. So the first part shows you the energy moves from left to right, especially wavefront also goes in the same direction. Here, the double negative or beta negative region, the energy moves from right to left, but actually energy moves from left to right. Wavefront moves from right to left, but the energy reaches the interface between the double negative region and the double positive region. So energy keeps flowing. So from the very beginning of the computational region of the structure to the very end of this computational region, energy is without any distortion reaches there, propagates there. So energy flows from left to right, but just for the wavefront in the double negative region, the direction is reversed or opposite the direction of the right-handed transmission line region. So you can make kind of a focal point making prism if you extend, if you just replicate this triangular region into the lower half, you can make this type of lens, which consists of an array of SRRs and an array of metallic rods. So double negative material plays the role of focal point making like this. And I'm proudly saying Tata's National Center for Radio Astrophysics, they use the concept I proposed several years back for designing their filters. So if you refer to my papers, well, and also their technical report and their journal papers include where the idea comes from. So left-hand side is my paper several years back, and the center is the technical report. They brilliantly adopt this idea to make VHF filters for radio astrophysics. I'm really proud of that. Good luck. And metamaterials are also used as absorbers. So I apply the design of the absorbers to cut the unwanted coupling between the closely spaced antennas. So you can see two printed dipoles. Actually, there's no metal backing for this antenna, and the other antenna does not have metallic backing. Actually, just a substrate-based printed dipoles. Dipoles do not have metal ground, as you know. So you have two, and you can see two antennas here, but the other antenna is hidden by the first antenna. When they are placed really close together, they couple. So as you see, S21, this is the port 1 given to dipole number 1. Dipole number 2 has the port 2. So if you turn on dipole number 1, especially port 1, from port 1 to port 2, you can experience very high interference, unwanted coupling. But if you can succeed in making a good absorber, as you see, the at 2.4 gigahertz, the isolation, the unwanted coupling drops very drastically. So this is the point where you can get, the far field pattern is not, far field pattern or the radiation of performance is not much affected by the other antenna for this antenna number 1 like that. And also you can make a absorber that can absorb the energy from 6 gigahertz up to 14 gigahertz, very wideband absorber. This is a 1-layer metamaterial absorber, which was physically implemented several years ago. Yeah, so I have talked about the the key features of metamaterials until now, but let me move on to the design examples for circuits and antennas. We designed a 8x8 Butler matrix a number of years ago. You can see 8 distinct beam patterns. These are the simulated beam patterns, and they can be measured. They can be compared with the measure results. So measure results also give us the 8 different beams. But this antenna is what the center frequency of interest is 28 gigahertz. So we had to reduce the size of the 8x8 antenna, 1x8 antenna or 8x8 Butler matrix to a very smaller one, as you see, taking advantage of the metamaterials. So you can see, well, this is the 8x8, but we tried, we started from a 1x4 Butler matrix, but 1x4 Butler matrix has been reduced with the help of metamaterial concept. And you can see 1, 2, 3, 4 beams from the measurement we can get. And you can compare how small the metamaterial feed structure is compared to the conventional feed network. So for the same frequency and for the same function, we could drastically reduce the size of the footprint of the feed network. So by using this small or miniaturized feed network, we could get 1, 2, 3, 4 directions of the beam. So, and we could observe the electric field flow and distribution for from specific blocks of this feeding network. And we tried what two-dimensional instead of this type of these are the one-dimensional array antenna, but we challenged the two-dimensional beamforming antenna with the help of the metamaterial concept. So you can see, so beam not like this. This is a 2D planar or 3D planar. Antennas are here, and the beams, you can get the beams like this. So two-dimensional beam forming is enabled by the metamaterial concept too. And we could greatly reduce the size of the 1x8 array antenna supported by the SIW Butler matrix to something very smaller. You can see the comparison between the sizes, but the functions are the same. So if you would like to put this antenna, actually, let me refer to the frequency of interest. They were aimed at radiation at 28 gigahertz, but the bandwidth is very wide too, such as 3 gigahertz or 4 gigahertz, if you dependent upon your skills of design. By the way, this size is much larger than the real handset. So if you would like to make a smaller antenna that can be insertable into one of the layers. Well, that antenna should be smaller. At the same time, that antenna, especially the feed network, should not be interrupted, electromagnetically interrupted by the other layers. So this project was supported by one global company in Korea. And we also tested how our antenna works with the, especially 5G antenna works with the LTE antennas. There are 1, 2, 3, 4 MIMO antennas working for LTE or for low frequency, such as 2.4 gigahertz or 3.5 gigahertz. If we want to have two antennas for 5G, such as 2 blocks of antennas with 3.5 gigahertz and 5G 28 gigahertz, you can follow this scheme too. So as you see, we can keep the independence of 28 gigahertz antenna function from the LTE MIMO antenna function too. So these are the far field patterns of the 4x4 MIMO antennas for LTA, and you can see 1, 2, 3, 4 beams from this 28 gigahertz antennas for 5G service. And we tested whether lower antennas can interfere with the 28 gigahertz antennas, but there was really little interference between very low frequency, such as 433 megahertz antennas, which are going to be used as a kind of a long distance paging, and a 28 gigahertz antennas for 5G. So as you see, when 433 megahertz antenna is turned on, the other antenna is not affected by this antenna. Furthermore, 28 gigahertz radiating elements are not interfered with by this antenna too. You can see the very blue area compared to the very hot look-alike area here. Sorry. I was really thirsty by keeping talking. Yeah, and we also designed another beamforming antenna. Actually, this is not for communication. This was for wireless power transfer. In Korea, wireless power transfer, like India or like the rest of the world, we are much intrigued in the projects or research topics for wireless power charging. So my antenna was used to replace a conventional large antenna. So as you see, layer by layer, they are really planar, and at the same time, you can make 5 distinct beams, or you can make more beams if you want to. And you remember this antenna, we could extend this antenna to form a base station antenna for femtocell or microcell in 5G, but the computation is very challenging. As you see, there are too many elements, but though this is quite time consuming, we are going to pursue the design of this. But the reason I brought this picture is, as you see, my antenna, this one, even though you stack up one antenna above the other, and when they are touched together, actually the interference between the row 1 and row 2, or row 1 and the row n, like that. This is what I'm trying to get. And we also designed, these are the real antennas adopted by one global company who funded the research project for us. We can make beamforming structures. There are 4 different cases of beamforming structures. We could also give the function to steer the beam for MIMO antennas, which works at 3.5 gigahertz. No one has imagined the MIMO antennas of 3.5 gigahertz can work as the beamforming structure, because the wavelength and the size of the antennas do not, the limitations to the wavelength or the size of the antenna doesn't allow people to give the beamforming function to the what MIMO antennas at sub 6 gigahertz, but we could do. And next topic is metamaterial antennas, especially metasurfaces, which change the diverging wave to the highly directed wave. So this starts with the fabric pearl cavity. So what this was published many years ago by my former student. He did the design of a fabric pearl or partially reactive surface, which could increase the directivity of the incoming wave like this. You can see a simple primary antenna, which is the microstrip patch. Microstrip patch basically has a diverging wave, but diverging wave experiences the n equal to 0 or near 0 metasurface lens. Actually, the diverging wave changed to a very high directivity. So you can see a structure like this. The beam width is very narrow, and the peak of the main beam reaches almost 20 dBs. So you, you have experienced the ordinary microstrip patch antenna giving such as about 3 dBis or something, but what the final gain is approximately 20 dBs. So you can increase the directivity of the beam pattern. At the same time, we added the diamond-shaped unit cells, which enables us to change the linear polarized incoming wave to a circularly polarized outgoing beam. So we could do both of the jobs with this structure before. And we observed the beam wavefront for my metasurfaces. As you see, primary source gives the energy here. If you put this type of a simple metasurface, actually you can tilt the beam. So the theta equal to 0 degree beam changes to theta equal to 20 degrees or 30 degrees. So well, you can twiddle the metasurface characteristics of the superstrate to your taste. And on the right hand side, this is what I mentioned before. The superstrate or metasurface should give us the n equal to 0 or n approximately equal to 0. Then you can change the diverging wave to the plane wave like outgoing wave. So you can see the outgoing wave after the superstrate or metasurface. This is the primary source which gives the divergent wave, but it becomes, the wavefront becomes very planar after this. And as I already explained, this diagonal shape can rotate the linear polarization to, convert the linear polarization to the circular polarization. And we extend this design to make a kind of a base station antennas for reality. So the circular polarized and highly attractive metasurfaces antennas can be made with the metasurface like this. We also used this pinwheel type unit cell for converting the divergent wave to the high directive wave. So this is another example, but this was tested for 5.4 gigahertz many years back. I presented this at IEEE APS, so many people were intrigued by the phenomena. The reason I am proud to just share this with you is the primary source itself is a minus first or negative first resonance mode antenna. So this is very small. Primary source antenna itself is small, and metasurface is metasurface. So we could combine the two metamaterial structures together. So we could get a success in changing the very wide beam pattern to a very narrow beam pattern. The byproduct was the gain increase. So around what 15 dBi, 15 dBis compared to a very low gain from the primary source. And also we could handle the beam tilting for two frequency bands such as 28 gigahertz and 38 gigahertz. This was so challenging that we could hardly accomplish within a very short moment of time, but we could do. And we also changed the cover material from the negative obstacles to a positive helper. So the 1x4 array antenna as the source antenna, when this source antenna is placed quite close to a kind of a radome structure or cover structure, the beam becomes very ugly. But if you make a metamaterial surface for this cover or radome, you can change the divergent wave or ugly wave to a very good looking wave like this. Gain enhancement is amazing too, such as 10.75 dBis, which is much larger than 1.45 dBis. And we also made the metasurfaces that can play the role of 1x8 array antennas for 1x4 antennas. 1x8 antenna effect is given by this metamaterial surface. So primary source is 1x4 array, but what we get is kind of a 1x8 array antenna effect. And we could make another metamaterial cover, which practically mimics the cover for your handset. So the source antenna, such as Qualcomm antennas and package antenna is used as a source, but your cover of the handset working as something very malignant. So you can make your cover something positive or something helpful. And here you can compare the negative effect of the cover or the radome structure is converted to something positive by designing the metasurface. Then you can compare the beams here. The low gain beam changes to high gain beam. And we could make a just reflector array. There are many possible references you can refer to for your reflector array designs in the future, but we use this. Especially we targeted at 28 gigahertz. So just horn antenna, this is primary source. This goes to the primary source of this reflector array. Instead of the curved structure, such as parabolic reflector, we use just a just flat surface, but the function is the function is the same as that of parabolic structure. So we could change the relatively low gain to relatively high gain, such as a 22.5 dBis. And MIMO antennas are going to be introduced. We designed zeroth order resonance, 2x2 zeroth order resonance antennas. Before us, people were very skeptical zeroth order resonance antennas or metamaterial antennas have negative results or consequences when we use them. But actually, I broke that prejudice. So zeroth order resonance, these two antennas were used as MIMO, and at the same time, I could add a decoupling network here to increase the isolation between these two antennas. This antenna was adopted to LG Electronics Materials Research Center, and they gave us the second year project to extend it to a very wide band MIMO antenna system. So we could get a success like this, very wide. The bandwidth is 400 megahertz. Another prejudice people had and the skeptical feeling was zeroth order resonance antennas cannot have a very wide band or practically wide band performance. But I also violated their prejudice before. So as you see, I can make very wide band antennas. These are the S11 and S22, and isolation between them, the coupling coefficients between them below -7 dBs or -10 dBs. So they were really satisfied with this design. And the third year project came to us from Electronics back then, many years ago. They want us to increase the number of density from 2 by 2 to 4 by 4, so we could do. So as you see in a journal paper, microwave journal, I prefer this journal for publications of my papers. So you can see the far field patterns, which are quite acceptable to the industrial use. And 8 by 8, there are two different types of 8 by 8 zeroth order resonant antennas. The shapes of these antennas are much different from those in the previous slides. Yeah, so we could experience the jump from the in terms of capacity or throughput in communication. The size of the platform is just size of the half wavelength patch antenna. But there, I could put 8 antennas. The isolation between them is around 10 dBs. It's amazing, actually. And return losses, or S11 or S8A, all they meet the requirement. So we could experience the jump of in terms of capacity from the CSO, or single input, single output, to 8 by 8 antenna here around 8 times higher. So this MIMO antenna is electrically driven, electric field driven. The other antenna is magnetic field driven. We also experience the same jump. So we could get a success in the increase in the capacity from the single input and single output case. When we use 32 by 32, the increase is around 400 times like that. And also we designed metamaterial feed structures for dual bands. So 2.4 gigahertz and 5.4 gigahertz. Only one structure, but this plays the role of the dual band feeding for the dual band radiating elements. And we made real MIMO arrays. Arrays and the MIMOs are different topics, separated. Just because you can see the placement of similar looking antennas, they are not array antennas. Array antennas should have the far fields from the elements interfering with each other in the far field, such as constructive interference and destructive interference, to have a main beam at a certain angle of direction, like that. Anyway, we could make a 16 beams from this antenna. This is the first ever. And what we also made were 4x4 and 8x8 sub-6 gigahertz and MIMO antennas, where we could increase the density. And meta surface, or this is a EBG. EBG is not always meta material, but this one is a meta surface, not using decoupling network or not using some kind of circuits. We just give the patterning on the surface of the substrate. We could increase the isolation level like this. Isolation level becomes changes from around 18 to 20s like that. So you can get the one-dimensional EBG structure and the two-dimensional EBG structure. And my students could could succeed in designing the metamaterial absorbers, very, very thin. You can see a dual band dipole antennas. So this is a port number 1 and this is port number 2. Before taking some steps, you can see the isolation level between port 1 and port 2 very high. But if we insert the absorbing structure right in between these two antennas, you can see 2.4 gigahertz and the 5.4 gigahertz. Well, these two frequencies have a very low coupling between these two antennas. Isolation has become very higher. Yeah, and I'm quite approaching the end of this talk. Yeah, here I would like to put the emphasis on the extension of the metamaterials area to EMI-EMC. EMI-EMC is not far from circuit designs or antenna designs. Actually, they live together with them. So here, this is the side view of the 5G antenna. This is the AIP, or antennas in package. This radiating element is connected to the RFIC, and you can see the ball grid array, and the pins of the IC are touching the necessary or related spots of back part of the packaging antenna. Here, the radiating element is fed through the inner conductor, and as you see, the RF signal starts from here, and while it moves, it experiences a lot of noise. So the noise, one of the source of the noise is the ground bounce noise. Ground bounce noise means power surface or power supply surface and the ground surface, they make the parallel plates. So the parallel plates cause unwanted resonances. These unwanted resonances trap the incoming RF signal when the signal frequency coincides with the resonance frequency. So this is a very, such a nuisance. So we would like to get rid of the pet peeve by giving the metamaterial surface inside here. So by the way, we took the very important part. We can carry out the full simulation for this full structure, but for the sake of simplicity, I just took the representative problematic layers like this. This is the input port area, which mimics the one of the pins from the IC, and the other side you can see the port 2, which is the feeding point to the radiating element. So this is the port 2, and this is the port 1. So port 1 comes to here, and the port 2 comes to there. So we hope the RF signal starting from port 1 goes and travels with no problem, not by being trapped by the parallel plates. They should survive the area and finally reaches port 2. This is what we want. I'm going to show you the before and after pictures. This is before picture. This is after picture. So without the meta surface, the energy, I intended to make the structure have the resonant frequency at 28 gigahertz. 28 gigahertz is going to, 28 gigahertz is injected, the signal is injected from at the port 1, and it travels, but it is trapped in the middle region, like this, in the middle region. So port 2 cannot get the signal here. So S21 or transmission coefficients becomes almost a null. Instead, at the frequency, simultaneously, at that frequency, the return loss or S11 becomes the highest. So energy cannot travel to port 2. So we can check the negative effect of the the EMI problem of the antennas and package. The eye diagram opening is very bad. It is very blurry. Soon you are going to see very wide open eye in the case with the meta surface. So here, impedance matching is very bad, and what far field pattern of the patch, actually port 2 is feeding this patch radiator. Patch antenna has very ugly far field pattern. You remember, you expect the very broadside far field pattern from the patch antenna when it is fed by the RF signal with good impedance matching. But if I give the good metamaterial surface as the filter here, we can introduce the perturbation into S21. So different from S21, from here, the red curve becomes the largest, or 0 dB. S21 becomes the almost 0 dB. That means transmission is the highest at 28 gigahertz. And S11, the black curve drops. So impedance matching is very good. So the energy is not trapped by the middle region. The RF signal from port 1 travels all the way through the via, and the top layer has the energy, and finally port 2, which is going to be connected to the patch antenna. Port 2 is good. So here, eye opening is good, and the broadside beam is observed. This is top view of the patch antenna, and the return loss, or S11, is very good. So based upon that EMC technique or troubleshooting solution, you can get 1x2 or 1x4 array antennas. Then you can tilt the beam as you want. And we tested the metamaterial circuit combined antenna in terms of the connectivity test. So this is the TX or transmitting antenna. On your left-hand side or top left is the wideband transmitting antenna, and this is the receiving structure, receiving radiating element that is connected to the triplexer of the made out of the metamaterial structure. So here, this is receiver, this is the transmitter. We can select the beam. We can select the channel. So if you send F1 or let me tell you something. In the sub-6 gigahertz, there are 3 mobile carriers. They are assigned 3 channels, right? One mobile carrier has 1 channel. F1, another carrier, F2, the third carrier, F3, like that. So for the sake of convenience, I'm calling them F1, F2, F3. So this receiving antenna, when F1 is given to the receiving antenna, we receive here, this is a transmission coefficient between these two antennas. You can see the peak at F1. And we alternate from F1 to F2 at the transmitting side, F2 here. The receiving side, F2 is selected. And F3 is given. And in the receiving side, we have F3 is received. And we tested then, we test the connectivity of the sub-6 gigahertz antenna system in my lab, and also we tested the far field performances in this unechoed chamber. But the last thing shows you something interesting. These are 64 COM constellation diagram. So when channel 1, the first row means transmitting signal is channel 1. And the second row is transmitting signal is channel 2. The third row is transmitting signal is channel 3. So what you have from the receiving side, channel 1 is the clearest and the clearest picture or clearest constellation. Meanwhile, the others, started to get blurry. And in the second row, channel 2 is received. This constellation is the clearest. And the third row, the channel 3 is the clearest. So you can see the digital signals are safely received by the receiving antenna based upon metamaterials. Yeah, that was a kind of a long run, and somebody might have been lost while I was giving very just wordy explanations on metamaterials or the basics. Yeah, let me briefly conclude. Yeah, metasurfaces cannot be the black magic for the 5G antenna solutions or 5G circuit solutions, but we can, after browsing and looking into the positive features of metasurfaces, you can combine them with the purposes of your 5G antennas or 5G circuitries. Thank you.
So,
Are you with me?
so really very nice talk, Professor Kahng.
Thank you.
I hope all of you are might be enjoying Professor Kahng's talk. Once you will interact with him live, maybe face to face sometimes, that will give much more inspiration and the way he works. So from our side, I would like to thank you. Also thank all attendees for attending this. When you are times maybe in Korea somewhere, let us see that. Yeah, Professor Kahng, maybe a few words from your side.
Words from my side?
Yeah.
Well, I'm really grateful to you for being patient until the end of my talk. Actually, this year I was really anxious to visit India, just not only for INCAP or international conferences, but also the meetings or conventions I could get together with my old friends or just new friends to be. Yeah, but well, due to this pandemic, what we were just prevented from moving around freely. But what online, we can see each other or we can hear from each other. Well, that's really fine. And thanks for giving me the chance to get connected to you.
Yeah, we will give you many more chance, Professor Kahng. So we will again come to you for many such things. Don't worry about that.
Yeah.
Okay, so in the last, I will give the dash to my head of department just to pass the thanks, so vote of thanks, and then we can conclude the meeting.
Mm-hmm.
Thank you, Amit sir. So I would like to thank the speaker and also all the participants. And last but not the least, the organizer, Dr. Amit Kumar Singh, and all the student team member and MTT chair, Dr. Saurabh Kusmanda, for organizing such a wonderful talk. And I believe that such events will keep on happening, okay, in next year as well. So I really would like to thank for your wonderful talk on this MIMO and beamforming. It was really interesting, and we got several things as a takeaway note. So thank you, speaker, and thank you all the participants for your patience and listening to this talk. And I assure you that we will continue such talks in future as well. Thank you.
Yes.
Thank you, sir.
Yeah.
Yeah, thank you.
Thank you.
So Professor Kahng, good night to you, and we'll again
Yeah.
come
Good
back to
night.
you.
Yeah.
Thank you.
Stay safe.